Welcome back, everybody.
Thank you.
So we're going to go over some questions on sections 4.1 and 4.2. Go back. Okay, hide that. This to go away. This to go away. And then hold this out here. Okay, which one did you say?
7.
7. Okay. So, and this is verify the function states the 3 hypotheses of Rolle's theorem on the given interval, then find all numbers C that satisfy the conclusion of Rolle's theorem. All right. Oh, did I just put that on the? I did. Whoops.
LOL, man.
Oops.
Crazy.
Silly. That's silly. Oh,
Oh, man. Now your day
what am I doing? Somebody's got a case of the Mondays. There it goes. You guys know that movie? Somebody's got a case of Mondays?
No.
Office Space?
No.
What? You guys don't know the movie Office
Yep.
Space?
Watch it.
No, it's definitely not School of Hard Knocks. We'll just say that.
Well, then why would I watch? I only watch
G movies. Oh, excuse me. Sorry, I forgot. Anyway.
The worst movie I've corporate drug Peter Gibbons. He hates his soul.
You're just looking it up on IMDb right now? Yeah, and it's it. Oh my gosh, that's like probably one of the funniest movies I've ever watched.
What's it called?
Office Space.
The best part was probably when he underwent fitness therapy.
That's the whole premise of the movie. He's like working in an office, and he hates his job, and he like goes to hypnotherapy to try to like feel better, and the hypnotist dies in the middle of his hypnotherapy, and they can't break him out of the hypnosis. So he's like walking around doing whatever he wants, and like he gets all these promotions because he just doesn't care. Like they're like, "Whoa, you're so forward thinking about all of these things." And then he like gets all those promotions. It's really fun. And then he ends up like stealing. All right, here we go. So f of x is equal to sine of x over 2, pi over 2, and 3 pi over 2. So if you want to verify Rolle's theorem, you have to say the 3 conditions. Remember, the 3 conditions are, here, let me pull it up here. 4.1. No, Rolle's theorem. Okay. It's got to be continuous. It's got to be continuous, differentiable, and have the same endpoints, right? It's got to be continuous, differentiable, and have the same endpoints. Well, is this continuous?
Yes.
Yes, this is continuous. Why is it continuous? Well, because it's a trig function, and trig functions are continuous everywhere. Right? I could plug in anything that doesn't matter. You know, x values are all real numbers. Range, well, it depends on how big or small the wavelength is, but or the amplitude is. But you know, x values, it doesn't matter. Differentiable. Wow, that is really good handwriting. It is differentiable everywhere as well, because it's always a smooth curve. Right? Think about a sine curve; it's always a smooth curve. So it is continuous and differentiable. The thing that we really have to check is f of a is equal to f of b. So f of pi over 2, and then we've got to find f of 3 pi over 2. Okay, well, so we find sine of pi over 2 over 2. Well, that's pi over 4. So sine of pi over 4. Well, Well, that's the y value at pi over 4, right? So it's radical 2 over 2. And then you do the same thing for 3 pi over 4. 3 pi over 2, but it will turn into 3 pi over 4. 3 pi over 2, which is sine of 3 pi over 4, which is the same thing. Radical 2 over 2, which means that f of pi over 2 is the same as f of 3 pi over 2. Okay, so there I satisfied the 3 conditions of Rolle's theorem. And then the direction said, then find all number C that satisfies the conclusion of Rolle's theorem. So Rolle's theorem then says that it says then there is a number C such that the f prime of C is 0. Okay, so I've got to find when the derivative is equal to 0. All right, so the derivative of sine of x over 2. So if f of x is sine of x over 2, f prime of x, well, remember that this is kind of like rewritten as sine of 1/2 x. Can I rewrite it like that? Right. So what I'm going to say is cosine of 1/2 x times 1/2. You understand why we're doing the times 1/2? Because it's technically a chain rule, right? So it's cosine of x over 2 or 1/2 x times 1/2 x or 1/2. Ooh, I think I didn't do the 1/2 in my key. Right, bro. Okay. Do I do the 1/2? Yeah, I do the 1/2. Okay. So we want to say when that, it goes away anyway. That's why it's, because if I divide over that 1/2, what happens? You get a 0 anyway. That's why I didn't write it. Cosine of 1/2 x is equal to 0, because when we divide by 1/2, it goes away. And then I take inverse cosine of the other side, so 1/2 x. And then I want inverse cosine of 0. Well, what is inverse cosine of 0? 1. Right? Inverse cosine of 0. Oh, wait. No, it's not. It's not 1. It's not 1. Whatever it was. Man, I lose my brain here. Well, what is... Oh, yeah. Jeez. When is cosine 0? What angle is cosine 0? Yeah, pi over 2 and then 3 pi over 2. Pi over 2 and then 3 pi over 2. Really? Right? So I have 2 different equations that I could evaluate. Am I restricted in my, yeah. Oh, I want both of them though, look. Pi over 2 and 3 pi over 2 is included within the interval. So I can say that 1/2 x is equal to pi over 2, and 1/2 x is equal to 3 pi over 2. I multiply by 2 over to the other side. That gives me pi and 3 pi. And I think, actually now I look at my interval. Is 3 pi within my interval? No. So 3 pi goes away. The only thing left over is pi. Whoa. No, it just said find the values of C such that it would verify.
So x equals pi, c equals
C equals pi, yeah. Yeah. Okay, what other questions?
12.
I hear 12. Sorry, there was some hands raised in the back.
Oh, my bad,
I
guys.
was gonna say 10.
You're gonna say 10? You're gonna say 10? Let's do 10 and then we'll hit 12.
Good with me. Right, wait.
Are we just gonna be doing problems all day?
Yep.
I mean, that's fine, we can.
Really just, that was tough.
Yes, W, how? Okay, so let f of x be tangent of f of x be tangent of x. Show that f of 0 is f of pi. But there is no number in C such that 0 to pi, such that f prime of C is 0. So basically, the derivative does not exist within there. Right? That's what we're looking at. Why does this not contradict Rolle's theorem? So let's take a look. First thing that we want to do is show that f of 0 is equal to f of pi, right? Okay, so basically, I want to find f of 0 and say, okay, that's tangent of 0. Right? When is tangent 0? When is tangent 0? When we've got 0 divided by 1, right?
No.
0 divided by 1, right? So it would be, what? The y coordinate is 0, the x coordinate is 1. 1 comma 0. Right? Where is that at? 1 comma 0. Oh, sorry, excuse me. So isn't it sine over cosine? Right?
Yeah.
1 comma 0. 2 pi and pi, just 2 pi, 0 or 2 pi. Because if it was on the other side, it would be negative. Oh, wait a sec. It would still be 0, wouldn't it? Yeah, it would, because it would be 0 divided by negative 1, which is still 0. So that works too. Right. Oh, but this is only from 0 to pi. But it's not included though.
That's why it doesn't contradict, so there's no interval
Ah, wait a sec though.
Later.
But any zero, wouldn't it just be?
Tangent of 0. Oh, I'm not doing inverse tangent. Duh, what am I thinking? Somebody's got a case of Monday. I'm not doing inverse. I'm trying to find the angle. I'm given the angle. The angle's 0. Oh my gosh. What the heck? What the heck am I doing today? Jeez. I'm not looking for the angle. I have the angle. What's the tangent at 0? When the angle is 0. What's the tangent? It's at that 1 comma 0, so it is 0. Right? Tangent of 0 is 0. I was working at it the wrong way though, because we were trying to find the angle. You're not finding the angle. It's not inverse tangent. It's just tangent. Tangent of 0. 0. Duh. Yikes. And then you find f of pi. And it's the same type of thing, but now we're on the opposite side, which is 0. Because it's at -1 comma 0. All right, so we verified that f of 0 is equal to f of pi. And now we say, okay, can this ever happen? Well, this is kind of what we were thinking before. We were saying, when does this, I think that's why I had it in my brain. I'll just make excuses for that. When does this happen? Well, this happens at pi, 2 pi, right? or pi, right? But The problem is, why does this not work? The problem is the premise does not exist, right? The problem is the hypothesis does not exist. Why does the hypothesis not exist? Yeah, but why does the hypothesis not exist? That's the conclusion. The conclusion is that f prime of c is equal to 0. But why does the hypothesis not exist? It's restricted, but how is it restricted? Because it's not inclusive, right? If you think about Rolle's theorem, I got it right here. If you think about Rolle's theorem, it's got to be in the included interval, right? It's got to be in the included interval. And 0 and pi are not included here. And the only places that it could occur are 0 and pi. So if 0 and pi is not included, it's not included within the interval, okay? So the only places it exists is within the non-included interval, so it doesn't even work. Rolle's theorem doesn't even apply, right? It doesn't contradict because it's the hypothesis is not there. You don't have the hypothesis. Okay, what other questions do we have? I heard 12 too, right? Let's do 12. The mean value theorem on this one.
Why do you have to find F0 if you know it's not zero?
Because it told us to show that f of 0 is equal to f of pi. That's why we did that. It contradicts it because it was not within the 0 and pi, the places where it could have happened was not within the domain. It was not within the interval that we asked about.
Those are the only two places you could have hit zero.
Right. Right. If it doesn't fit the hypotheses, it doesn't contradict the theorem because it never actually applied in the first place. Let's take a look here. Come on. All right, here. Verify the function satisfies the hypothesis of the mean value theorem on the given interval. Then find all numbers C that satisfy the conclusion of the mean value theorem. So the mean value theorem is different from Rolle's theorem because the mean value theorem has doesn't have the restriction of f of A is equal to f of B, right? It just says that it's got to be continuous and differentiable. There we go. Yeah, mean value theorem says that f is continuous on the closed interval A to B, and it's differentiable on the open, and there is a number C within A to B such that f prime of C is equal to the slope between those two endpoints. Or you've got it in that point slope form, f of B minus f of A is equal to f prime of C times B minus A. All right, so we first have to say, okay, is this continuous? Oh, what the heck is that? Okay. Is this continuous? Yes. Why is it continuous? Because it's a polynomial. And any polynomial function is continuous everywhere. Is it differentiable? Yes. Is it differentiable? Yes, because again, it is a polynomial. And polynomials are also differentiable everywhere. So it fits the hypothesis, and now we state the conclusion. And the conclusion is that there has to be a number in f prime of C, or sorry, in between A and B, such C that f of B, and I like to do the point slope one, f of B minus f of A is equal to f prime of C times B minus A. Okay, so let's find it. Let's plug in this is f of 2 minus f of negative 2, f prime of C, B minus A, 2 plus 2. Okay, so let's evaluate it out. Let's plug in f of 2, 2 to the third, minus 3 times 2 plus 2 is 4. F of negative 2, got negative 2 to the third, that's where, to the third, minus 3 times negative 2 plus 2. That's 0. F prime of C, I'll write it as f prime of x, is 3x squared minus 3. Times 4. All right, so let's just evaluate now. 4 minus 0 is 4. Let's divide over the 4 to get it over to the other side. That gives me a 1. Add the 3, divide by 3. I get 4/3 is equal to x squared. And I square root it. I get plus or minus 2 over radical 3 is x. Do both of them work? Let's check. 2 divided by radical 3. Because I got plus and minus that. Yeah, that both of these fit within our interval, don't they? If I'm going from negative 2 to positive 2, since the decimal value of this is about 1.15, both of them work. Right? So that's my answer. Yeah, plus or minus 2 over radical 3. That make sense? What other questions do we have? Could come from section 4.1, 4.2, doesn't matter. 20 on 4.2? Okay.
When is this quiz?
Well, that's a good question. Not this week. I did get verification. There are going to be 4 tests within this semester. There's going to be a 4.1 to 4.4 test, a 4.5 to 4.8 test, 4.9 all the way to 5.4 test, and then 5.5 through the end, 6.1 test. So there are 4 tests. And I read a little further into it, and I kind of checked with somebody. The final exam is comprehensive, which means it's the full year final exam. Because it's a full course final exam.
Wait, what?
I know.
No, super tight. No, that's not medical.
So, yeah. I saw that and I was like, oh, that's new. But don't worry. We'll have an exam review. We'll plan accordingly. Don't worry. You said 20, correct? Oh, I didn't even copy it. Sorry. Oh, this one. Show that there's only one real root. This was kind of funky. So again, what we have to show here when you're showing that there's only one real root, is that you have to show that there is a root. A root does exist. And then you have to show that not only if there is a root, that there could be more than one. Because I've got to say only one real root. And this kind of ties in to section 4.3, honestly. And you'll see why here in a second. Okay, now, because this is x to the third plus e to the x, right? Think about e to the x, number to the x power, exponential, right? And think about x to the third. Those are continuous everywhere, correct? Because x to the third is continuous and e to the x is continuous. So I know it's continuous everywhere from negative infinity to positive infinity. So as the function goes, like think about it as a graph, x to the third plus e to the x plus e to the x. Is it 6? Oh, no, come on now. Okay. So it looks kind of similar to x to the third, right? Just the simple cubic. Do you see how it goes down on the left and up on the right? Right, the whole end behavior thing, it goes down on the left and up on the right. We know the limit as x goes to negative infinity of, and let's let f of x equal x to the third plus e to the x, just for our notation. The limit of f of x as x goes to negative infinity, well, it went downward on the left, right? Is negative infinity. Likewise, on the right, f of x goes up, goes to positive infinity. So we're saying here that on the far left side, it goes down. On the far right side, it goes up. We used it in class last week, but that intermediate value theorem says that if I go far left, then it's down, and if I go far right, it goes up. There must be some point. Call it negative infinity on the left side and positive infinity on the right side. There must be some point on the left and on the right that it crosses through the x-axis, as long as it's continuous, right? And we know, we talked about how it preserves continuity, right? Because it's x to the third is continuous and e to the x is continuous, so it's continuous everywhere. There's no gaps or breaks. So it is continuous everywhere. And in my response on the homework, this is all like written out, saving me from writing this, I'm just talking about it. It's continuous everywhere, so therefore that I know that if it's continuous and I can pick a point on the left and on the right, that it will, one's negative and one's positive, right? This is negative, the output is negative, the output is positive. One output is negative, one output is positive. It has to cross the x-axis somewhere, right? So there must be a root. There must be a root somewhere in between there. So using the intermediate value theorem and the fact that it goes down on the left and up on the right, it shows that there is one root. Okay, it shows that there is one root. Now, if you look at the derivative, now we're doing, okay, showing that there is only, there's only one possibility of a root. There can't have another root. Right? Look at the derivative. 3x squared plus e to the x. Is that ever negative? No. It is always positive. So it's always positive for all values of x, no matter what. Anywhere on any x value, I think it's always positive. It can never go into the negatives. So since it's always positive, it's always increasing. Meaning the slope of every tangent line is always going up. Because that's really what the derivative is, right? The derivative is the slope of the tangent line. So if the slope of the tangent line is always positive, it will never come back downward, right? The function will always be going up. And we can see that in our graphing calculator, right? The function will always be going up. If I calculate the slope at any given point in there, it will never be negative. It will only ever be positive. It could be 0 as well, because it looks like there's an inflection point in there. Well, not an inflection point, but a leveling out point somewhere in there. But it never goes negative, at least. Right? So therefore, we know that there is only one root. Whoa. Again, if this was on a quiz or test, I'd ask you to write that out a little bit more, which is what we kind of talked about, but. Okay, what other questions do we have? Yes.
What sections will the quiz next week be over?
4.1 to 4.3. Basically, whenever we finish section 4.3, I want to give a day or two of review just to kind of go over homework problems and stuff, and then we'll have a quiz over that. Those 3 sections. Yeah.
We're going to review that or the homework's already due that?
I haven't decided that yet. I know what we're doing today and tomorrow, but beyond that. I know we're going to do section 4.3. And then beyond that, I know we're going to have a quiz over that, whenever that happens. But yeah. And I know there's a test eventually out there in the distance, once we get past section 4. All right, any other questions on the homework? Anything else? Okay, all right. Let's start section 4.3 then, just a little. Oh, we only got 5 minutes left today?
Yeah, yes,
You
sir.
started late. You're talking a lot.
But I was letting you guys check your homework. Sure. All right, well, tomorrow we will start section 4.3. Okay.